I want to prove this relation using mathematical induction. So this is the left hand side and this is the right hand side. I want to prove it for any n greater than equals to 1. So since I will use mathematical induction, the way is to first I will see if this can be proved for n is equal to 1, which is the first natural number as it is said. And once we can do that, what I will do, so let me do this one first. So when n is equal to 1, left hand side is n is 1, so 7 into 1 minus 4, so that is 7 minus 4, and that's 3. And the right hand side is, so that will be n over 2, so that's half. 7 1 minus 1 there, so that's half, and then 6 7 1 is 7 minus 1 is 6, so that's 3. So it is true for n is equal to 1. Now we will do an inductive state, that is we will assume that n, for n is equal to k, which is k is any natural number, this relation is true. We will assume that, and we will try to prove that if this is true, we will see if the relation is true for n is equal to k plus 1. So if we can do that, that means when k is equal to 1, which we have already done the proof, then the relation will be true for n is equal to 2, because when k is equal to 1, this is we are assuming, and then when if that is true, which is we have done, then this is true for k is equal to 1, that is n is equal to 2, and similarly it keeps going on for any n greater than 1. So that's what we will do. So first we will assume that the relationship is true for n is equal to k, where k is any natural number. So that becomes here 3 plus 10 plus 17 plus up to 7k minus 4 is equal to k k over 2. So basically this one, k over 2, 7k minus 1. So this is true, we are assuming. Then we will see what happens when n is equal to k plus 1. Let's see the left hand side. So that becomes plus 17 plus 7k minus 4, and then 7k plus 1, then minus 4. So that we are assuming here. And then once, so it is, this bracket is not needed actually. So this first part is actually this one, because we have assumed that n, when n is equal to k, this relationship is true. So this whole thing is this one. So this is k over 2, 7k minus 1, plus here if I get rid of the bracket, it becomes 7k plus 7 minus 4. So that one is k over 2, and then 7k minus 4 minus 1, plus here it is 7k plus 3. So plus 7k plus 3, that's there. So this one becomes 7k square over 2 minus k over 2 plus 7k plus 3. So this one is 7k square over 2 minus, this can be written as 6.5 or 13 over 2k. Let's leave like that as a fraction, and then 3. So that is a plus here, because this one minus this one. So that's the left hand side. Now let's look at the right hand side. When n is equal to k plus 1, that will become, our right hand side is k over 2, so k plus 1 over 2, and then here it's 7k minus 1, so 7k plus 1 minus 1 there. So now we have that. So this one will become, I will rewrite actually, so like that, sorry, 1, and this is 7k plus 7 minus 1. So k plus 1 over 2, and here it is 7k plus 6, 7k plus 6, and this one, this is k over 2, So it can be written 7k square over 2 plus 7k over 2, and this one is plus 6k plus 6 over 2. You can write like that. So this is 7k square over 2 plus this one is 7k over 2 plus this one is 3k, and this one is plus 3. So I'm just dividing this thing, writing separately. So this is 7k square over 2 plus this one is, if I just add it, it will become 7 plus 6, so that's 13k over 2 plus 3. So I can see this is the left hand side. The left hand side was this one, and the right hand side is the same. So is equal to left hand side. So we have proved this one, that if n is equal to k, the relationship holds. If for n is equal to k, then we see that the relationship is true for n is equal to k plus 1. That means the k is any natural number greater than 1 or 1. So when k is 1, the relationship is true for 2. When k is 2, the relationship is true for 3, and so on. So this way we have proved that this given relationship is true, and this is this method is called mathematical induction. I have done another problem previously, but this is just one more, and I intend to do few more later.